Okay, students, let's dive into our Chapter 25, EM induction and EM waves. Now, induced currents. Well, Michael Faraday probably has made some of the greatest contributions to electromagnetism of her time, along with James Clerk Maxwell. Maxwell's equations helped to revolutionize the understanding of electromagnetic waves and their properties. But Faraday was the first one to actually experiment with inducing currents. And so basically what he did is he took a iron magnet and wrapped a coil of wire around it, and then wrapped a coil of wire on the other side, hooked it to a amp meter, and when he closed the switch, he saw a brief, momentary impulse of current go through the meter. And so what he realized is that current could be generated if you could change the magnetic field that the coil of wire was passing through. So what he did then is that he took some wire, wrapped it around an iron ring, or just took some coils of wire and passed like a solenoid and passed a magnet through it, back and forth, and he realized that when he did this, it would produce current, okay? And we call this an induced current, okay? Now, that's it in a nutshell. So you take a magnet, you pass it through a coil of wire like a solenoid, you will induce a current on the wire. Okay, if any of you have ever bought one of those Faraday flashlights where you shake it, basically what you have is you have an iron rod, which is basically a bar magnet, and a coil of wire, and that coil of wire slides up and down on the permanent magnet, and they put a little capacitor in there, and you charge up the capacitor, and then when you're ready, you just use the flashlight, okay? And that's what we call magnetic induction. All right, now, or inducing current by magnetic induction, okay? So what is motional EMF? Well, it's what it says it is. It's voltage or current that is produced by moving a conductor through a uniform magnetic field. So we call this motional EMF. Now, of course, we know how to find the force produced, do it every time. We know how to find the force produced by a magnetic field, the charge, absolute value of the charge, times the velocity of the charge, times the magnetic field, and then of course sine theta. And of course you want it to be a 90-degree angle where you get maximum force. So we just leave the sine off because sine of 90 is 1. All right, now, so if we take this conductor and move it through this magnetic field, then we induce a current on that, and because of the force created, magnetic force created as we move this conductor through a magnetic field. Because remember, what is voltage? What is current? Well, we know current is the amount of charge through a given time interval. And again, I told you when we talked about current, it's actually the volume of charge. And of course, voltage is the work done on the charge, and you can't do work if there's not motion, okay, kinetically. Now we can do it chemically by moving of electrons, but it's still motion involved, okay? And so we can find then the electric field strength of a motional EMF based on the velocity of the particle times the magnetic field. So if you want to know how strong the electric field is, if you know the speed of the charge, then the magnetic field, you can find it, okay? Excuse me, okay? All right, now, what about the voltage? Well, the voltage, we add one more element in here. We add the length of the wire. So the motional EMF, and I hope you're writing these equations down, to find the voltage through a conductor that's being moved through a magnetic field. Then we can take this times the length times the speed times the length times the magnetic field to find the actual amount of voltage, okay? And here it is written in a little different term using the symbol for EMF, okay? So EMF due to motion is the velocity of the conductor times the length of the conductor times the magnetic field, okay? And it's just that simple. Of course, that's why you want to, and we're getting a little ahead of myself, you know, that's why generators do not turn at very slow speeds. You want it to turn at a very high speed, okay? Because you can produce a lot more voltage, okay? All right. Of course, two ways to generate EMF, like I said, through a battery, the movement of electrons in a battery, and also moving a conductor through a magnetic field, okay? All right, so what we do then to do that is they put this U-shaped rail on there, and you move this conductor back and forth, and we induce a current in the wire. And so how do we find induced current? Well, if you remember from Ohm's law, the voltage divided by the resistance, well, since it's motional EMF, we use our motional equation for voltage, for E, for EMF, and divide it by the resistance, and therefore we can find the induced current. And of course, that's in amps, so you can write that on your formula card, okay? All right, so what about induced current in a circuit and the amount of force of the magnetic field? Well, to find that, we do what? Well, we remember from a previous equation, this equation right here, if you remember the force in a magnetic field, well, let's do a little bit of substitution here, and let's do some substitutions here for current. Okay, substitute for current, and so looky here, notice what happens, that it becomes what? The velocity of the conductor times the length of the conductor squared times the magnetic field squared divided by the resistance, okay? And of course that is how much pull, force pull, which is equal to the magnetic force, okay? And so notice they're equal, and that's how you can find it using this equation right here. So here's another one you need to write down on your card. And again, that's just showing you how it would work if you were pulling or pushing, okay? All right, now, what about power? Okay, well, we just take those equations. If you remember when we found power, easy way to find power, of course, from Newtonian, it was the force times the velocity. Well, okay, if that's the case then, let's plug that in, plug in our variables, and notice it's the velocity squared. Okay, you see they go back and take force from that previous equation, put it into this equation. Notice it becomes velocity squared times the length squared times the magnetic field squared divided by R, and that will give you the power input. And then, of course, power dissipated, same thing. Okay, it's exact same question, exact same equation, all right? So what is a generator? A generator, of course, is anything that turns mechanical energy into electric energy. And you say, well, how do we do that? Well, we just spin a coil of wire in a magnetic field, and we have what are called slip rings and brushes, and here's a good diagram to show you the basics of a generator and how it works. Notice the direction of your magnetic field. Now notice it's moving this way, and the current of wire, or the wire, is in this direction. So we induce a current because look, the current and the magnetic field are perpendicular to each other, so therefore we can induce current when the wire, the surface of the wire is at a 90-degree angle with the magnetic field, or the area of the loop. The area of the loop is normal to the magnetic field. And so we produce current that way. All right, of course, there's the brushes. What are brushes? They're just pieces of carbon, graphite, and they touch these slip rings, and these slip rings, of course, are connected to the coil of wire, and we are able to move the current that way. Okay, and of course, as the wire turns, the signs change, and we get alternating current. All right, magnetic flux. Well, he found, of course, that current was induced when the amount of magnetic field passing through a coil of loop changes. Okay, well, that's one way we can produce flux. But what about another way? Okay, if the coil of wire, or if you change the area at which the field passes through, then guess what? Then you can create more flux or less flux, okay? And just like they use a fan blade here, if you adjust the blades on a fan as to whether you want to produce a lot of air or very little air, well, the same applies with magnetic flux based on either the motion of the material in the magnetic field or changing of the magnetic field. You can do it that way, or you can change the size of the loop in which the magnetic field is passing. Okay, and here we see, notice that the magnetic flux is always going to be maximum when the normal now, and by the way, this is the area, okay, the area normal, the area of the loop is normal to the magnetic field. Notice that the normal is parallel to the magnetic field, but please understand something. In actuality, what you have here is the actual material itself is perpendicular to the magnetic field. So it all depends on what variable we're talking about. Are we talking about the material, the loop of wire, or are we talking about the normal to the area of the loop of wire, okay? Because this is a 90-degree angle, and of course this is actually in the same direction as the magnetic field, so that would be a 0-degree angle. So what does this mean? Well, if you go back and look, this would be the one where it's this way, where it's perpendicular. The wire is perpendicular to the magnetic field, which means that the normal to the area is parallel to the magnetic field. This would be the smaller area. Notice that it is tilted. So this is actually how much area you would have passing through. So how do we find then the effective area? Well, it's AB cosine theta, or just plainly written A cosine of theta. And notice it's cosine, not sine, okay? So again, same from the side, same tip. Now this is, notice the angle is 0. Cosine of 0 is 1, isn't it? So you get maximum magnetic flux when the coil or the loop or whatever it is perpendicular to the field, in one in which remember now, the normal to the area makes a 0-degree angle with the magnetic field. In other words, it's parallel, okay? Here it is tilted, so you're not going to have as much flux. So we come up with the equation of magnetic flux being the area efficient, or the efficient area, times the magnetic field cosine of theta. And of course, if the magnetic field is this way, okay, and our material is this way, that is maximum flux. If the magnetic field is like this, okay, and again, why? Well, because it's perpendicular to the field, or the normal to the area is parallel to the magnetic field. Okay, if it's like this and the material's right here, guess what? Okay, this is flux max, and this right here is flux is equal to 0. Because notice that the material forms the normal forms a 90-degree angle with the magnetic field, and so therefore the cosine of 90 is 0. Okay, so there's another equation. Of course, the Weber is the unit of flux, and it's a Tesla meter squared. Okay, Tesla meter squared, or a Weber. That's the unit for flux. And again, still talking about the angle, how the angle makes a difference. Now, What about Lenz's law? Well, Lenz's law has to do with an induced current in a loop of wire when the magnetic flux through the loop changes. So in other words, here we're looking at changing flux, okay? We're not necessarily changing the wire per se, this area of the wire, but we're talking about changing the flux. We could be. And so Lenz's law basically says what? Basically three things it says. That the magnetic field through the loop changes in area. Okay, I said it didn't have to, but it could. And then the loop moves into or out of a magnetic field. So you got three ways here in which we can create flux, and so we can change the size of the loop, we can change the angle, or we can move it in and out, okay? Okay, now, so here we see Lenz's law. You take this bar magnet and you push it down, and as it approaches the amp meter, you know what's going to happen? It's going to move over here, isn't it? Sure is. It's going to move that way. But when you back it up, guess what's going to happen? When you move the magnet back up, the amp meter is going to go negative. It's going to go in the opposite direction. Well, that would stand to reason, would it not? Because you're moving backwards, okay? You're moving backwards, all right? Okay. So Lenz's law, again, you determine the direction of the magnetic field that it passed through, and then how much the flux is changing, increasing, or decreasing, okay? Then, of course, determine the direction of the induced magnetic field that will oppose the change in flux, okay? All right, and then you can read that. I'm not going to read it to you, okay? Okay, now, Faraday's law. Okay, so when we look at Faraday's law, remember we've already talked about how he discovered that if you took a magnet and you passed it through a coil of wire back and forth several times, that it would induce a current. So current induced, or motional current, you could call it that, motional current or EMF current, is simply put what? Well, it's the EMF source divided by the resistance, okay? All right, and of course, again, we determine the direction of the current by Lenz's law. Remember, if the magnetic field is moving downward, then the needle moves positive. If it's moving upward, then it moves negative, okay? So Faraday's law says what? That the EMF of a loop, okay, is based on what? Well, the change, now notice something here, the change in flux through a given time interval. Not just flux, but change in flux, okay? And that's very important, okay? So if the flux changes through a given time interval, then we create what is called EMF or voltage, okay? And so if you have a coil of wire that has a certain number of turns, then this is how we would find the actual EMF of the coil. You just take the number of turns times the change in flux per coil divided by the time interval that it is the flux is changing in, and you can find the EMF of the coil. Of course, another equation there. So there's two fundamentally different ways to change a magnetic flux through a conducting loop. You can either move or expand or rotate, creating motional EMF, or you can change the magnetic field. I mean, that's, hopefully you've seen that as we've gone through all of this. It's basically, there's two ways to do that, okay? By changing the size of the loop, turning it, rotating it, or by changing the magnetic field, okay? All right, so that's simple. Of course, electromagnetic induction is where we take Lenz's law and Faraday's law. Lenz's determine the magnitude, and Faraday's determine the magnitude, and Lenz's to determine the direction, okay? And again, our electromagnetic induction, where we see the change in flux divided by the time interval, okay? And again, we've already been over that. All right, I hope this helps.